Welcome to our How Tall Is That Bar Chart talk. This was work led by Diane Watson while she was an intern with us in the HCI and Visualization group at Autodesk Research. And Diane is the expert here and on the call, so she'll be ready to answer your tough questions when we're done. So as VR technology continues to improve, we're seeing more interest and more great research looking at general purpose data visualization in VR. But as we make visualizations in VR, we need to look into how some VR-specific phenomenon might affect our perception of these visualizations. One such phenomenon is called distance compression. While in a VR environment, when shown an object at a given distance, people tend to unconsciously underestimate the distance of that object. This is a well-studied and well-known phenomenon. This could, of course, be a problem for data visualization in VR. For example, if shown a very tall bar chart like this, would you underestimate its height in VR? Rather than just showing the distance compression affects visualizations in VR, we want to see if there are ways to mitigate its effect. To do this, we set up a study that looked at two variables that might affect the amount of distance compression experienced. The first is the depth cues used in the visualization, and the second is the scale of the visualization. So first, considering depth cues, the most basic chart in VR has no depth cues, no textures, no ground plane. However, the lack of a ground plane tends to make people nauseous in VR, so we did not test this condition. The first depth cue condition we did test is called few depth cues. In this case, the objects had a consistent luminance and no texture, and there's a simple textured floor plane underneath the chart. The next condition is called some depth cues, where the bars were given a slight texture and they cast shadows from the light. We'd consider this a best practices chart for designing visualizations in VR. This has potentially useful cues without anything too over the top. And then we have a third condition called rich depth cues. And in this case, the scene is augmented with objects that could be used to determine relative size, such as trees and cars and light poles. So the other variable we're looking at was scale. And so to begin with, we have what we call personal scale. And so in this case, the entire visualization could be seen at one time while looking straight ahead. The next scale is called house scale, where the participant needed to look up slightly to be able to see the entire chart. And then finally, we have what we called skyscraper scale. This is an extremely tall visualization requiring the participant to look way up to see the top of the chart. And to study this, we had the task, and in the task, users were asked two questions. The first, what percentage of the large bar is the smaller bar? And then also we asked how tall is the smaller bar in real world units, so they could answer that in feet or meters or whatever they wanted. And so from this first study, the main interesting takeaways were that around 77% of all height evaluations were underestimates, which confirms that distance compression was indeed generally happening for height evaluations. And secondly, and sort of interestingly, the average error on the height comparison task was only 9.7%, which suggests that while distance compression was a large issue on the absolute value estimation task, it was less of an issue in the comparison task. When we looked at depth cues, so the style of the rendering in the charts, actually the performance varied very little across the three depth cue conditions that we looked at. However, interestingly, 81% of participants thought they performed the best in the rich depth cues environment. That's the environment with the trees and light poles and etc. So we ran two more studies beyond that first study. The second study is looking at how people could move around in a VR environment to look at charts. So having different platforms and elevators and set viewing locations to look at the chart. And the next was looking at different types of charts in in VR to see if they have the same properties that we found with bar charts. And so from these studies, we were able to produce a set of 6 design guidelines for presenting charts in VR, which we hope will be useful for future designers and researchers in this area.